second from the math that we did. We're going to talk about how we can look at models to help us figure out this concept of equilibrium. So this reaction that we have, if you were able to print out the notes, I apologize if you don't have color printing. Mine don't. There are two different colors here. And we're not going to assign what the different atoms are. We're just going to say that the blue and the purple atoms are different. If you're colorblind, I apologize for that as well. So when they're mixed together, they form those two new compounds where the purple gets replaced by a blue to make something new. And so when they're two mixed together, initially we have this many amounts of all of them. And so in a second, like later on down the page, you see the initial conditions. You can actually count them if you really want to know how much is there. But initially we don't have any reactants. So the forward reaction will spontaneously happen to make products. So we can figure out what the equilibrium expression will be. Now this number 16 is just an assumption that the equilibrium constant will be 16. Okay? And so this 16 just says that the constant width equals 16 for the ratio when we take the concentrations of all of the different molecules involved. And n is the number of those molecules. So initially we have these amounts. It's a little bit farther down. There's 9 of the 3 blues and 12 of the 1 blue, 1 purple, and then those are the 2 reactants and then no products. So let's see how we can reach equilibrium. So just assuming that we have 5 molecules transfer, and it's a 1-to-1 ratio for everything that on how it works, from the initial to the new conditions, all we have to do is we know that it's going to shift towards the zeros. So that's why we're adding for the products and we're subtracting for the reactants. We get these 4 new values for the molecules. So then we can plug into the expression to see if that will equal K. Well, if you plug in the numbers, it solves to be 0.9. So no, that means that it is not at equilibrium. So because it's not equilibrium, it doesn't equal 16. So since it's less than 16, that tells us that it's going to shift to the right. So we need to make some more products, make the numerator bigger, so that we can get the ratio to be more like 16. Okay, so instead of just plugging in an arbitrary 5, we can say that the number of molecules that needs to change is going to be x, like we've done in 7.7 with our ice charts. So x amount of each have to disappear or form to reach equilibrium. So then we can substitute this into our ratio, and then we can solve for x. So we actually will have to do quadratic formula here to get it to solve. But if we simplify this right here, that's what I'm looking at, we will have 16 is equal to x squared over, ready for these big numbers? 9 times 12 is 1728 minus, then 21. Oh, sorry, no, I was looking at the wrong number. My bad. It's going to get bigger. It's 108 for 9 times 12. And then minus 21x for the 9 plus the 12, and then plus 2x. Okay? And so then getting that denominator out of there and multiplying everything by 16, this is where the 1728 comes into play. Minus 336x plus 16x squared equals x squared. Okay, so plugging in for quadratic, when we get a 0, I'm just going to put my 0 equals here, it'd be 15x squared, because I subtracted this one over. Okay, minus 336x plus 1728. So then setting this into the quadratic formula, I can show you. Contact me if you really want to see it. The two options for x would be 14.4 or 8. Okay, well remember when we did the quadratic before in 7.7, you have to pick the correct x that makes it not be a negative number at equilibrium. So if we go back here, looking at our equilibrium conditions, if I used 14.4, both of my reactants would be negative values. So that's not possible. So that means that we're going to say that x is equal to 8. Okay, so then when I plug 8 in for these conditions, then that means that I'll have one of the 3 blue molecules left at equilibrium, and I'll have 4 of the 1 blue, 1 purple, and then I'll have 8 of both of the products left over at equilibrium. So when this picture shows that, you can take your time to count if you would like to, all of those. But the whole point of this section is just to help you see that even though maybe we don't have specific conditions with molarities, we can still use these pictures, these models, to help represent the relative amounts before equilibrium and at equilibrium, and the process is still the same.